Okay, cool.
Hello, everyone. I'm Oliver, and I'm going to talk about a project that I'm calling Printegrated Circuits. It's something that I've been working on in my PhD. I'm a human-computer interaction researcher at the University of Bristol. And what I've been doing is sticking PCBs into 3D prints to try and make this kind of scalable and easy to replicate kind of interactive device. So this here, no. Yes. Okay. This also is an printegrated circuit, and it's a bit dodgy. So this here is the tune shroom. I have one right here. What it is a printegrated circuit, and inside there's a PCB, and in that PCB, and then there's also this. It's been printed in conductive PLA as well as non-conductive PLA, and so the black spots are actually touch sensors, and then inside, there are these traces that lead down to a Seed Studio Xiao ESP32 microcontroller. And so you've got, this conductive filament that's creating connections that allows you to use it as a MIDI controller. So let's see if this works. That was fun. Thank you. So this wasn't the original tune shroom. This actually started out as a project, as a PCB. This was back in 2019, and I wanted to learn about how to make electronics, how to make PCBs, how to make high-fidelity electronics that you can make a lot of, give to your friends, maybe even sell. And so I set out this, it was mostly a learning project to make the tune shroom, which was a PCB-shaped mushroom. So it started out as a Weetabix box with some aluminium tape, as all good projects do, and it was connected up to this Arduino Pro Micro. And then I took that design and brought it into KiCad using the SVG to Shenzhen plugin to make this really cool shape. These two steps I really enjoyed. Kind of, you get quite a lot of control over the design. You can iterate and try things out. But then the next step is to get it made, and that's always really daunting. I find you have to click this button that says "Pay Now," and then you have to wait 2 weeks until your project finally arrives. So how can we make high fidelity prototyping more local, more like crafting, more like the first two steps of this project? So that's where I think 3D printing comes in. So 3D printing electronics isn't something new. There are a bunch of companies out there who are trying to do this, but at a really big, or like at in research labs and other places that have lots of money. So this is the Voxel 8 that was a project that injected like silver paste onto circuits, and then this is the Bot Factory, which uses inkjet printing to try and print PCBs there in one single machine. But what about the technologies we already know? I'm a really big fan of FDM 3D printing, or FFF, so which is the extruding hot plastic, a bit like a glue gun. And these technologies are becoming really advanced, especially in homes and makerspaces and places that we as hackers kind of have access to. So we've got this machine in our lab that in the university that it's a multi-tool machine that can print with different materials, and these are becoming much more common. And then there's also this conductive PLA that you can buy from Protopasta that allows you to combine non-conductive and conductive structures to make weird sensing things. So there are two big issues with this. Resistance is one. So making conductive plastic is quite difficult. Resistance of this material is advertised as 30 ohm centimeters. What that corresponds to is the traces that I showed you earlier in the tune shroom. They're about a 1.5 millimeter by 1.5 millimeter kind of cross section, and that's about 50 ohms per millimeter. So in the whole length of the tune shroom, you've got about a 7 kilo ohms between the board and the pads. But that's enough to do various sensing things like this capacitive sensing that I'm doing here. It's also anisotropic and depends very much on how you print. So if you print in long lines, it conducts better along the layer lines, and also it's more resistive in Z than it is in X and Y. Resolution is another issue. So the microcontrollers that we love, like the RP2040, have a very fine pitch and are designed to go on PCBs. This is like a 0.5 millimeter pitch, whereas the nozzle of your 3D printer If it's got a stock nozzle, it's about 0.4 millimeters, and so you've not got enough space for a conductive trace and a non-conductive trace. But so the solution to that is to use kind of existing PCBs that have wider spacing on the through holes. So this is the Raspberry Pi Pico, which is kind of the breakout dev board for this chip, and you can print traces that have that spacing. So why not have the best of both worlds? So why can't we have 3D printing, the high resolution and low resistance of PCBs, and the free form nature and the rapid reconfigurability of 3D printing? So how do we make one of these these Printegrated circuits? We're going to use the example of the ladybird here. I really like my cute little examples. So this is a media controller. The little buttons allow you to play and pause your music, or skip a track, or increase the volume. So inside, you've got your PCB that's embedded, and I've designed the whole thing in CAD. This is in Onshape, and I've designed the conductive, the places where you want conductive filament as a separate part from the non-conductive filament. So then when you're printing, you need a cavity for your PCB to be placed in. You pause your print. Ooh, oh no, something went terribly wrong. I'm gonna unplug that guy. We're gonna revert to the working slide clicker, because the slide slug is temperamental. So you pause your print.
You were changing slides with
So you insert your PCB like this, and then you resume printing. But then when you resume printing, there's a special step, which I'm calling prinjection, another made-up word, where you inject a small amount of conductive filament into all of the through holes. This creates both a mechanical and electrical connection between the traces that you then print. And so you come over the hole, and then you inject a small amount and wipe off to avoid any stringing that might happen. Here's a nice little video or a GIF of that happening. Quite low res, because GIFs. And then you print the traces over the top. The plug, as I said, it kind of acts as an anchor. If you don't have that there, the trace won't stick to the surface of the PCB, and it'll just peel up, or it'll be very unreliable. So here's a cross section of a PCB that I've cut in half. One on the left side, we've got a non-projected hole, and on the right side, we have one that's been filled in. And as you can see, there's like very little contact on the left side and much more on the right. So once you've printed your traces over the top, you've got something that looks like that, and then you finish the print, and you get a cute little ladybug or whatever you've printed. So the design process, I start in a CAD software. I use Onshape because it's nice and browser supported. And then I slice it in Prusa Slicer. But then after slicing, there's this important step, which is to get the projection movements in there. So you need to tell the printer where you need to tell the slicer where the holes are to have the filament injected in there. And then have it insert those movements into the GCode file that is used by the printer. So I've got this, I wrote this slicer post-processing script, which is very ugly. This might be the video that doesn't work. We can see. Oh no, that's great, it does work. This is it in Prusa Slicer, just in its original form. You can see the cavity inside. And then I press when I export GCode, it opens this other program. And this is my awful thing that's based on Prontoface, which is a wonderful piece of open source 3D printing software. And then I'm opening the drill file from the PCB that's been being inserted. And then it has the coordinates of the holes to inject the filament in. And then once I'm happy with that, I press the Printegrate button. And then once I'm happy with that, I press the Printegrate button. I'm a bit slow. I really want to get it lined up. There's no way, I haven't found a way to get it to automatically know where to put the holes there. And then you can see these gray lines on top, which are the movements of the printer after it's finished printing, after the pause command's inserted. I think that's just going to go on a loop. No? So one of the questions I feel like maybe is being asked is, can we recover the electronics after we've kind of permanently embedded it inside our 3D print? The answer is yes, sort of. You can use a hot air gun to heat up the plastic. It's PLA, so it has a kind of glass transition temperature about 50 degrees, and it'll start getting really, really easy to take apart. at the kind of temperature that a hot air gun will be, and that's a bit lower than the temperature of the solder that's on the PCB that you're doing. So it's unlikely that you'll damage the PCB in the process. After doing this, so then you've got your waste bit of plastic, but you can reuse the PCB that you've inserted. And then we had a go at like recycling the filament. The interesting thing here is that when you recycle filament, you want to put a bit more virgin material in just so that it prints nicely. And then even with that small amount of black conductive filament that's in the print, all of the stuff that comes out is like completely black. It's amazing, but it's not very conductive. There's this idea of a percolation threshold. So inside this filament, there are all these little small bits of carbon black. And when they're not close enough together, they'll have a very high resistance. But then after a certain point where the kind of networks of conductiveness can form, then you get a much higher conductivity. So now I'm going to talk about some other cute examples. This is the IOSA pod. It's a human input device for a computer for sending emojis to your computer, because everyone needs one of those. When you stroke it one way, it sends happy emojis. If you send it the other way, or if you stroke it the other way, it sends angry emojis. This is the slide slug. Well, this was the slide slug until it failed on me. Used to be wired, but then I was like, oh, I want to make it wireless. And it's got a little battery in it that I inserted afterwards. But yeah, a similar idea. So this is a whole family of little printegrated circuits, but they all kind of work the same way. They're a little capacitive touch device that's a human input device for a computer, and they have this kind of touch sensing capability. Most of them I'm using the Seed Studio Xiao board that I was talking about earlier. It has native capacitive touch sensing capabilities, so you can just have a single trace that goes to one of the pins on that board. But there are other things you can do. So you can also do contact sensing of a sort of kind. So I made this bistable switch mechanism that allows you to kind of create switches and things. So you could scale this up and have a load of switches in a device. Or even you can do resistance sensing. So you can do create a voltage divider and create a potentiometer of sorts. So I use this in the snail sense. This is a plant pot moisture sensor. So it measures whether your plant needs watering or not. And yeah, it measures the resistance of the soil. And if it's been watered recently, then the resistance will be lower than if it was watered more. Yeah. Here it is in action. And so yeah, you can see the resistance go down as you add water. This is another device. This is a habit tracker of sorts. And using Lego bricks, you can stack them up to make different towers. And then the device itself is able to measure how many bricks there are in each tower based on the resistance. So each of these bricks has a very thin conductive trace between the two sides, and that it acts as a resistor in a parallel ladder. So as you add bricks, it reduces the or it divides the resistance, and then you can count how those work. Here's a nice web interface that I wrote for it, and then it can keep track of things. So why do I think this is exciting and interesting? So I said earlier I was an HCI researcher, human computer interaction researcher. What we do a lot of the time is we create these interactive devices and then we give them to people and then we study how they work. And a lot of that involves making more than just your Arduino prototype. It needs to work like out in the field, and someone needs to just touch it. Okay, bad example with the slug, I guess. But and you want to make a lot of them, but not like enough to make it worth going to a factory and getting them mass produced. So I'm thinking, maybe 3D printing is the way to do this. And recently, I had the opportunity to go to Shenzhen in China, which is this amazing place. Everyone should go. And it's where most of the world's consumer electronics gets made. They've got these huge markets and loads of factories that are all producing this stuff. And there's this really strange ecosystem that produces weird things like this. So these are Shanzai phones. They're this kind of counterfeit, creative way of making weird electronics. And they're all basically the same microcontroller on a board inside an injection molded case. And so, while I was in China, we also got to visit all these different factories. Oh, yeah, sorry. This was part of the Research at Scale residency with Cedric Honnet, who is one of the Oshawa people. So we visited this factory. There was a Flex PCB factory on the top floor of this building, and they had these these machines that were putting stiffeners on flex PCBs, like really expensive, really fast, amazing things. And then downstairs, they had these huge machines for making injection molds with like electrode discharge machining technology. So yeah, huge things. And so with that, with kind of access to these tools and materials in Shenzhen, they're able to make these really weird and wonderful little niche devices for very specific use cases. And I wonder if maybe there's a similar thing to be said for the amazing tools that we're now starting to see that are popping up on our desks. What if we can, start using these machines to make all sorts of other weird things? And then what else can we use these technologies for? So thank you very much for listening to my talk. I need to thank the Pro Squared Network Plus because they let me go to China, or funded my trip to China and some of this research. And I also need to thank the other contributors to this work, Ollie Hunton, Jack Dawson, Steve Hodges, and Mike Fraser, my supervisor. Yes, thank you very much. If there's time for questions.